So, on our agenda today, don't forget there's mastering tonight. We're going to do a group quiz on Friday. I have your individual quizzes to get back to you today. And then you have an exam soon-ish. It's 3 weeks from today. It's not the week you come back from spring break, it's the week after. So, let me give you some words of warning about this exam coming up, right? Exam 2 covers the chapter we're on, the last chapter, and the chapter before that, 14, 15, 16. Do you remember what was in chapter 14? Yeah, little k's. Everything about little k's. Yeah, what's a little k? It's a little k's, right? So everything about little k's is going to be on the test, as well as everything we've done about big k's. And so you may want to start going back and reviewing some of that over your spring break. I know that sounds like a bummer, not for me. Chemistry over spring break sounds amazing. But, right, I think the issue for exam 1 was that when you saw the question, a lot of you guys were like, that sounds really familiar, and then you spent a lot of time thinking about the question instead of answering the question. So you need to be able to come into these questions, because I'm going to ask the same ones that are either on mastering or on the quiz. They're going to be worded the exact same way. You should be able to see the question and be like, buffers, I know, write this out. Or I come into it and you're like, oh, she's asking a titration question. Start writing. Like, the question should be so obvious, there's only one way to solve it. You just start. And that's only going to happen if you do lots and lots and lots and even more practice. Every time. They're assuming you have a book, which is correct. It's under the Resources tab. And all the KAs and the KBs are in the textbook. They're assuming that you have this thing that has pages. Yeah. All the information for so if the KA and KB are not given, they're assuming, apparently incorrectly, that you have a textbook and you know how to operate it. Because all of the KAs and KBs are in the chapter. They're in a table in chapter 15. It's all in chapter 15. There's an appendix also. Yeah, it just depends. All the Ks and KBs are in the chapter in a little table, but they're also in the appendix. So you could look to both places. Oh, okay. Yeah. It's in there. So, on your homework for tonight, if you come across a question, you're like, a KA or KB would be very helpful to solve this, it's in the book. That's where they're assuming you're going to go look for it. So, yeah. All right. Let's do one more buffer problem before we move into titrations. All right, so here I have a buffer solution that was prepared by adding 4.95 grams of, what is that? It is sodium acetate, right? And the clue should be, right, it's with acetic acid and it's a buffer. So that's its conjugate base. They're in there already. I realize there's an extra H in there, isn't there? Yeah, S. We didn't calculate it, but we talked about it. Yeah. I can do that at the end if there's time. Here are my pile. And really, it's going to be the same question we're going to do here. It's just a combo. All right, so first question, I want to figure out what is the pH of the buffer initially. What do I need to do? A few options of what we could do first to figure out the pH initially. We could certainly write out an equilibrium statement. That's a good idea. Okay. So acetic acid and water Okay, that's not a bad statement. That's good. Doesn't help us find the pH yet. Because let's say I wanted to fill in the ice table. What kind of information do I need now to fill it in? Well, not molarity. I need moles. So I need to find the moles of everything. So I need to find, wow, I picked two really terrible markers in a row. Alright, so I need to find the moles. Alright, which one is easier to find from the information given right this second? Which one can I find right away? Acetic acid, right? You have everything you need to find acetic acid moles. Easily. You can find the other one. So if I want to find moles of this, right, 0.150 moles. Yeah, if you don't have your calculator out, definitely get it out. We're going to be hardcore calculator today. So understand, it's easy to trust me that I do it right. I'm going to say that's a false sense of trust. There's a good chance I'm going to mess up. Alright, so I have that many moles of the acetic acid. Now, the question is, I want to find moles of this guy. I have given you all the information you need in order to find it on your own. What would you have to do? You'd have to determine the molecular weight. I'm not going to have you do that this time. But you do, right? I gave you the formula, right? Sodium's 32, 12, 1 each, 12, 16 each, 1. You certainly could figure out the molecular weight. I'll go ahead and tell you. It is, I guess I'll put it up here, 82 grams per mole. All of it, right? Because when you weigh it out, the bottle will say it's sodium acetate. You can't have a solid that's a charge by itself, right? So like acetate would have a minus sign, but you can't have a minus sign exist really by itself. So the weight, like you guys do in lab, right? You did in lab where you weighed out, I think you do sodium acetate, and the molecular weight in the bottle includes the sodium as the mass. But then when you do this, it would really be, sodiums would be on both sides and then cancel out. Yeah. Good question, though. Alright, so now I have 4.95 grams. Make sure that's right, 4.95. Alright, so now I have moles of both. So now, what should I do to find the pH? Knowing it's a buffer. Yes, use my HH equation. So we're at the point that I now know moles of conjugate acid base, and I'm looking for pH. What's the one piece of information that if you had your textbook, you could certainly look up? Ka. So I'll just go ahead and tell you. Alright, so what do I need to do to be able to use my HH equation? Yeah, right, I need this pKa. So the pKa is negative log this. Alright, so you're going to over break, you're going to do so many of these problems that you're going to just in your head be, oh, what's the pH of a buffer? Okay, I need to find the mole. I need to write down Henderson-Hasselbalch. I need to find the pKa. I need to plug it in pH. And you're on to the next problem. So it comes second nature, right? Okay, pH equals 4.74 plus log. Which one was the base? This number 1 or number 2? 1 or 2? Which one's the base? Number 1. So put that on top. We have a base. Is this pH more acidic or less acidic than the pKa? Less acidic, more basic. Does that make sense with our mole ratio? It does. Good. Excellent. So that's part A. Question, Abigail. Well, you could solve for the pKa. Right, if they gave you 2 out of the 3 things, yeah. Or I could look it up. Oh, so you can totally solve for that. If you know these 2, you would subtract, raise both to the power of 10, then you're left with x over 0.375. Yep. Alright, so here's my question, part 2. I'm now going to add 82 milligrams of sodium hydroxide to 100 milliliter aliquot. What does it mean, aliquot? Yeah, it's just a fancy word meaning like sum of. But sum of is wordy, so we want to sound snooty. So we're going to say aliquot, obviously. Next time you're out and you want to impress your friends, say, I would like an aliquot of pizza, please. And that would be 1 slice. Right? Or, you know, however you want to use it and drop it in some conversation. I think it makes you sound very impressive. My husband doesn't think so. He thinks I sound ridiculous. But I find myself hilarious. So, I laugh at myself. Even if I was like, that was funny. It's like, Alright, so the question is, does it matter? No, let me do. Yeah, no. Let's do this first. Let's first write out. Oh, so this is part C. Okay, so this was our original equation when it was just in water. What do I now have to write my equation to be that I am going to add some base to it? Does the base react with the acetic acid or with the sodium acetate? It reacts with the acid, and I've provided the Ka. Where should the acid be, as a reactant or a product? It has to be a reactant, right? I've given you the Ka, so it has to be an acid. So you know it has to be the acid. So that's how you know what to pick, right? You know you have a strong base. The strong base is going to react with the acid. And I've given you a Ka, which means acid has to be the reactant. Alright, so now I've got that set up. What is it? Can I use the Henderson-Hasselbalch equation right this second? No, because I don't know the new equilibrium concentrations anymore. So if I can't do the HH equation, what do I now have to use? An ice chart. If I'm going to use an ice chart, ice table, what do I need to know about the sodium hydroxide? Mole. I have to know moles of it, right? So I have 82 milligrams of sodium hydroxide. What do I need to tell you about sodium hydroxide? Molecular weight, it's 40 grams per mole. So somewhere, I guess, off to your side, wherever you want to write it. try and leave myself a very good spot. I'll do it down here. Why? I gave you 82 milligrams. Why did I write a 0 point? You have to put it in grams, right? Okay. That could have been tricky. That's no, maybe. Alright. Does it matter about this 100 milliliter aliquot for my ice chart? What part, like if I'm putting it into here in moles, does it matter how much liters I have? No, right? It's just in moles. So the moles that were in 250 milliliters are the same number of moles that were in 100 milliliters, which is why we do it in moles. Doesn't matter the volume of the container, because the moles are going to be constant throughout both samples. Okay? So by doing it in moles, we eliminate any of the issue about changing volumes for now. In like 20 minutes, it'll matter again. But for now, it doesn't matter. Alright, so now we're ready to fill my ice chart. Oh, is this an ice chart or an IACE chart? This is an IACE chart. Because it says added. So you have added something. So if it says, so I'm going to say the trick to these questions again is going to be reading comprehension. Alright, where you read the problem and it either says the word buffer and you're like, you need to use the HH equation, or it's going to say something was added, in which case you need to make this kind of chart. Right, because the added is right here. So it's just going to be getting in the habit of like looking for keywords. Buffer, added, equilibrium, something like that. Alright, so now we're ready. Alright, so I know moles of this. I had it up here. There it is. Initially, we don't have any of that. And we initially have. It's okay if I don't have any more water. Alright, now I have this many moles. I didn't add any of that. I added this. Alright, now, what do I do to my acetic acid? Yep, you subtract it off. What do I do to my hydroxide? Subtract off also. What do I do to my acetate? I now add it. Now, let's see here. Alright, so now I have equilibrium concentrations. My original question is, I want to find the pH. What do I need to do now, right? Because now I have concentrations of conjugate acids and bases. What is this solution now, if it has just conjugate acids and base in it? Now it's a buffer. What do I do to find the pH of a buffer? HH equation. Now we're ready, so we can plug it back in. And since it's the same solution I have, the pKa is what we calculated earlier. And what's that? Is this pH more or less basic than my original solution? More basic. Does that make sense? Yes, right, because we added base. We would expect it to be more basic. Is it a lot more basic? Not really, right? The buffer's doing its job. It's like 0.05 more basic. The buffer was able to eat up all those extra hydroxides. How do you feel about that? Okay, so what we're going to do is take this kind of problem and now apply it to a titration where I'm not adding just one shot of base. I'm going to add base over a range of milliliters. And we're going to see how the pH changes as we add more base. But it's going to be exactly what we just did. Here we just did one shot. But I would like to know what happens if I add a little bit of base, more base, and predict what the pH does. Okay? Let's do that. The fact that everybody's eyes just went, ooh, it'll be okay. It'll be okay. It'll be okay. Alright, so titration, right? It has the burette, has the little stopcock at the bottom with the flask, right? And the flask changes color. Usually, I think all the ones you do are pink, right? Clear to pink. There's lots of options. In my environmental chemistry class, we just did blue to purple. And then we're going to do orange to red. There's one other one we do. I think it's green to blue. So indicators come in all different colors. It's just the ones you guys typically use are clear to pink, because that's the most obvious, right? It's either not colored or colored. The blue to green is a little trickier to see. Excellent question. Let me skip ahead a few slides. It is slide 16, so we can skip ahead and we'll go back. Alright, so a pH indicator, right? The stuff you're using, the phenolphthalein, the 3 or 4 drops that are critical to put in, and you know for sure when you haven't put it in because you've titrated 50 milliliters and nothing's happened, and then you have to tell your lab partner, sorry, totally forgot to put in the indicator. We're going to be doing this again. Usually your lab partner is okay with it, depending on what time is left in lab. So an indicator is a compound that is itself a weak acid or a weak base, in which case it's making its own kind of buffer in solution. So for example, right? So you have an indicator that's a conjugate acid base with itself. So the indicator protonates the acid, and it can deprotonate and be the base. Let me think for phenolphthalein. I think this is pink, and this is the not colored. You could call it clear. It'd be scientifically incorrect. It just doesn't have color. It's either colored or not colored. You can use clear. That's fine. And so, if it is this, means I can also write a statement like this. Right? I can use the Henderson-Hasselbalch equation to describe an indicator. Totally fine. Okay, what happens if we are at the point where the concentration of pink and not colored are equal? Okay. right? That would also be true. If I get rid of the p's, the little p's, pH equals pKa, or the concentration of the acid equals the Ka, right? Just getting rid of the p part of the equation. It's a weird sentence. P free without p. Sounds good. Alright, in which case, if these two are equal, that's right when you're starting to titrate, and like it looks like it's pink, and you give it a swirl, and the pink goes away. That is right here. That these two are, the concentrations are equal to each other. And so depending on what type of titration you're doing, this should be the one where I think we need to add, I think we add base. I'm setting it up so we're titrating base into it. It's been... Yeah. If we're at a point where the pH value is less than pKa, right, so your solution is still very acidic. You've not added enough base. What's the color of your solution then? Clear, right? Because we're at the point that it's still not colored. So you haven't added enough base to get it to turn over yet. There's still a lot of acid in your solution, so nothing's happening. So this is really what happens first, right? Nothing's happening. Then you get to the point, this point right here, where at the pH equals to pKa. You're real close, like it turns pink, and then you're like, I did it. And then your partner swirls it, and then it goes away, and they're like, oh, we didn't do it. So you keep adding. I taught a lot of labs where two partners are like, one's like, I did it, and then the other partner picks it up and moves it, and all the pink disappears. And they're like, no, we didn't do it. The worst is when you have a colorblind partner, right, and then they can't tell what's happening at all. Like, they can kind of tell, but not really. Don't ever put that person in charge of, like, seeing into the flask. They're in charge of note-taking. That's their job. So it's not rude if you ask your if your partner's colorblind. Be like, hey, before we get started, can you see the difference between pink and not pink? So, totally fine. Oh. Yeah. Alright, now we're to the point where the acid is less than the Ka, or the pH has a value greater than the pKa. What's going on now with your solution? There is more base, in which case it is now, hopefully, pink. For phenolphthalein. Yes. So the indicator has its own pKa. And so, for example, the titrations you guys typically do in lab typically have a pH change in the 7 range. Like, that's how you know you're done, like it's 7-ish. Well, you can't see 7, right? And so you could have your pH meter in there, which I think you guys do this. You do a pH meter titration, where you stick the meter into the flask, and you just keep reading the numbers until you reach whatever value. Or if you pick an indicator, like phenolphthalein, if its pKa is right at the pH you're expecting the reaction to be done at, the color will change. And if the color changes, it tells you, oh, I've finished the titration. You could, yeah, that's a possibility. And so, depending on what you're titrating, that's why my lab isn't titrating stuff that has a pH of 7 when it's done. Our lab was looking at, the experiment was over when the pH was 9.2. Well, I can't use phenolphthalein because at 9.2, it's already pink. it'd be pink the entire experiment, which would not be helpful. So you need to pick an indicator that changes color around about where you know the experiment's over. So the question should be, how do you know when the experiment's over? Let's calculate it. So how do you know? Like, how do I know in advance that the pH change will be 7 when we're all done, or 9.2? How did I know that? By being able to calculate in advance things about my reaction. So a titration, even though it seems very boring, right? Doing a bunch of titrations it doesn't seem like cutting edge science. It is still one of the most powerful and accurate ways you have to determine concentrations of acid or base in solution. So still, lots of people do titrations as their everyday job. There's some machines to help you out, but in general, just a guy doing some titration. So if you love it, there is a job out there for you. If you love titrating, there's companies out there that's all they do. All right. All right, so there's some things we need to know before we get started on calculating. The equivalence point of a reaction. So the equivalence point is where the moles of the two reactants are both equal to each other. So where one reactant is completely consumed by the other reactant. So everything we've done until now, right, one has been used up, but we still have some of the other one left over. The equivalence point is where there is 0 reactants left over, equal moles. So they cancel each other out. It could, like, the ratio would be 1. Right. If I was looking at the fraction, that ratio is 1. We'll do one like in 2 minutes. Yeah. Okay, that's all right. It may be easier if we calculate it and then you can see what I mean. All right, so let's say I'm titrating sodium hydroxide into hydrochloric acid. Alright, strong acid and strong base. If I make a strong acid, strong base combo, what are my two products? Salt and water, what should be the pH? 7. Right? Because I've used up all the strong acid because it reacts completely with strong base. All that's left is water. pH is 7. So let's calculate why that's true. Right? You just told me it's true. Absolutely true. We're going to now calculate a titration and show the equivalence point of 7. So we're going to do a strong acid, strong base titration. What are some key words in my question that tells you things you need to be able to do for this problem? Slowly added, right? So if you see the word added, what do you need to do? If it's an IACE chart, what do you first need to do? Moles. So the word added should tell you the kind of chart, which then tells you moles. What's the other thing you need to if I didn't have this title across the top? What else do you have to recognize about this problem? Right? I have a strong acid. Oh, question mark. I meant, what am I using? NaOH. There. I should probably have a proofreader for my notes. Alright, so what happens to the pH is I add hydrochloric acid to 50 mils of 0.1 molar sodium hydroxide. Alright, so the word added tells you IACE chart, and that chart tells you moles. Alright, the other thing you're going to want to picture in your mind, based on this phrase, which solution should be in the Erlenmeyer flask? The NaOH, right? Because you're not doing any with that. So this word conjures up, that's terrible looking. You know, that's the Erlenmeyer. Something like that, right? That's really what burette looks like. Pretty much that. Right? So this like 10-word sentence should tell you a bunch of information. 1, strong acid, strong base. 2, it has to be the IACE chart. 3, if it's that chart, it has to be moles. And the volume of 1 is going to be, the sodium hydroxide is definitely in the bottom, the HCl is being added to it. Okay. I know, it's an action-packed sentence, right? Alright, so let's look at the point where I've added 50 milliliters of the 0.1 molar HCl to the 50 milliliters of sodium hydroxide. Alright, we already decided we need to do an IACE chart. So what do I need to do in order to set up an IACE chart? I need the equation. So what are my two reactants given this is a strong acid, strong base? We're going to leave out the extra letters though. So what? OH minus. And then how do we tell the reader that's an acid? H plus would be good, but it'll be wacky with my equation. So we're going to use that. If you use H plus, it would turn out okay. Right, if I had done this, that's not wrong. I just always write as hydroniums just so that I'm always in the habit of using hydroniums. Both are fine. Alright, so now what do I need to do to fill in my little chart? Moles, right? I need moles. Right? So if I have 50 milliliters of 0.1 molar NaOH, you can see how these problems get very confusing. There's just like a lot of stuff that you have to calculate that don't necessarily go into the chart. So you want to be able to like keep track of all labeling. It'll be very handy. So, alright, so that's moles of sodium hydroxide. How many moles of the hydrochloric? Oh, question first. Yes. Yep. Mhm. Mhm. We happen to know we're at that point. Plus, it's a strong acid, strong base. But if you wrote double arrows, that's totally fine. Yeah. Sure. So I have N. Right. If I wanted to write it like this, that'd be fine. Right. That's technically what's happening. But then what do we do when we have equations like this? You cancel out the things that are on the same side. Really? Right? Because sodium hydroxide doesn't exist as sodium hydroxide. It exists like this. Right, so the things that aren't, right, because that's a strong base, so it completely dissociates. The sodiums or chlorines don't count in my final thing. I prefer H3O. If you wanted to write it as just a plain H, that would be okay. It would just be one. It wouldn't, because this is water. And the number of waters don't matter. Yep. Questions on that? Okay. How many, if I have this many moles of sodium hydroxide, right, I would do the same thing to find the hydrochloric acid. HCl, 3.0, 1. Why did I? Alright, so I have gotten to the point that I have initially added, let's see, okay, so here we are, right? Initially, just in our flask, we have this. Right? That's what we initially have. We have just sodium hydroxide, no acid. And I've added acid. They are both on the reactant side. So what do? We minus both of them. So what do you have left in your solution? Not nothing. Just water. And salt, right? Because that, technically there's salt still in there. So if it's just water, what's my pH? There's salt, but the salt doesn't have any effect on the pH. pH is a measure of this. It's just going to be ions floating around. You could get to the point that they would crash out, but people who invented English called it salt, and we just went with it. No, I think it probably was one of those episodes where it was edible, and they called it salt because it flavored their food. And then we're like, oh wait, it's a chemical, like everything, right? And it's this kind of form of thing. So, question. I would say it would be up to you. Like if you knew off the top of your head, oh, you might have to calculate moles. I'm like, oh, moles are equivalent, strong acid, strong base, pH is 7. Done.
Okay, so like you don't have to calculate the
No, I just did it for this one because when we come back on Friday, we're going to make a table of different volumes and then a graph. Graphing. You thought we were done with graphing. Not even close. Graphing's making a rapid comeback. I have your quizzes give back to you. If you're able to